A Taylor polynomial with a degree of k can be written as the sum of the derivatives of a function f of x on n factorial evaluated at x equals a on the factorial of n multiplied by the difference between x and a to the power of n. So we said that this Taylor polynomial for the function f is centered at x equals a, and it can thereby be used to approximate the values of the function f in the x equals a. So in this case, a is equal to pi on 2, and our function is cosine x. And you can see that when we use a 0th order polynomial, we have a really bad approximation to the function. And we can see that the linear approximation approximates cosine x better in the x equals a. And as you keep using more terms of the Taylor polynomial, you get an even better approximation, even further out from a. So these terms fn here are just the function and its derivatives. So when n equals 0, we have the function evaluated at a, and when n equals 1, this is the first derivative evaluated at a, and so on. Let's find a 4th order Taylor polynomial approximation for cosine x about x equals pi on 2. So our function is cosine x, and we keep taking derivatives up to the 4th order derivative. And now we evaluate the function and its derivatives at x equals pi on 2. And now we can write our 4th order Taylor polynomial approximation for our function. So that would be minus 1 on 1 factorial by x minus pi on 2. And we've also only got a 3rd order term. So that would be 1 on 3 factorial by x minus pi on 2 cubed. And the rest of the terms are 0. So as we can see, for a 1st order Taylor polynomial approximation, we have a straight line. So the linear approximation is very good, close to pi on 2. And it gets worse as you move away, as we can see. But the 4th order polynomial approximation has a cubic term, so that gives a much better approximation to the cosine function.